Hello everyone, this is Yulin Wang. I'm glad to present our ICCV paper, Adaptive Focus for Efficient Video Recognition. Recent years have witnessed an explosive growth of online videos. By 2022, online videos will make up more than 82% of all consumer internet traffic. More than 300 hours of videos are uploaded to YouTube every minute. Such large amount of data has fueled the demands for automatically recognizing human actions, events, or other contents within videos. Many realistic applications like recommendation, surveillance, and content-based searching will benefit from this automatic video recognition. The good news is, in addition to images, deep learning is still an effective solution for video recognition. Deep networks have achieved impressive performance on large-scale benchmarks like kinetics. However, processing videos with deep models is far more inefficient than images. In the left of this slide, we compare the computational cost of several popular video recognition models with their corresponding CNN backbone. One can observe that processing videos may lead to even 75 times of flops. In real-world scenarios, computation directly translates into power consumption, carbon emission, and practical latency, which should be minimized under both economic and safety considerations. Therefore, a key challenge is how to make deep learning-based video recognition more efficient. A straightforward idea is to leverage the temporal redundancy. Most existing works focus on allocating the majority of computation to the most task-relevant video frames rather than all frames. However, another important source of redundant computation in image-based data, namely spatial redundancy, has rarely been explored in the context of efficient video recognition. One can observe that not all image regions in each frame are equally informative. Ideally, once we can focus the computation merely on some relatively small but task-relevant spatial regions of video frames, the inference efficiency can be significantly improved, since the computational cost of deep models typically grows quadratically with respect to the input size. Here our question is, can this spatial redundancy be leveraged to facilitate efficient video recognition? If the answer is yes, it should be compatible with the existing temporal-based methods, as we can naturally focus on the most task-relevant image regions of some important frames instead of all frames. To answer these two questions, we propose an adaptive focus network, namely AdaFocus. We assume that a stream of video frames come in sequentially. Our method first takes a quick glance at each frame with a light-weighted global CNN-FG to obtain cheap but coarse global features. Then the features are fed into a policy network pi to predict the location of the most informative image patch. We crop the patch, activate a high-capacity but computationally expensive local CNNFL to process only this selected region. Due to its reduced size, considerable computational cost can be saved. Finally, we concatenate the local and global features and feed them into a classifier FC to get the recognition results. Notably, both the policy network pi and the classifier FC are recurrent networks. They work by aggregating the information from all the previous frames. In brief, our method allocates computation unevenly across the spatial dimension of video frames according to the contributions to the recognition task, leading to a significant improvement in computational efficiency with the preserved accuracy. To ensure the four components of AdaFocus work as we designed, we introduce a three-stage training algorithm. At first, we remove the policy network. and randomly crop the local patch to train the two CNN backbones and the classifier with the cross-entropy loss. In this stage, the model learns to extract task-relevant information from an arbitrary sequence of frame patches, such that we can evaluate the importance of different patches with the behavior of the classification parts of the model, laying the basis for learning the patch selection policy for AdaFocus. Then we introduce a randomly initialized policy network Pi. Fix the three classification components and train Pi individually with reinforcement learning. We model the patch selection operation using a categorical distribution, which is parameterized by the outputs of Pi. During training, at each frame, a patch will be sampled from several candidates. Then a reward will be obtained to tell the policy network how well this patch is. The action with the large rewards will be encouraged, while the actions with low rewards will be inhibited. At test time, we simply use the patch candidate with the largest categorical probability. To calculate the value of rewards during training, we feed the selected patch into the local CNN FL and the classifier FC to get the corresponding softmax probability on the ground truth labels, PTY, and compare it with the average results of randomly selecting patches by subtraction. Intuitively, we hope to encourage the model to select the patches that are capable of producing confident predictions on the correct labels with as fewer frames as possible. Formally, the parameters of Pi will be optimized by maximizing the sum of the discounted rewards over the time. Here we use the off-the-shelf PPO algorithm. Finally, we fix the global CNFG and the policy network Pi to fine-tune the local CNFL and the classifier FC with the learned patch selection policy. The optimization objective is to minimize the cross-entropy loss. This stage is not fundamentally essential, and it is designed to further improve the performance of AdaFocus. As aforementioned, our method can be augmented by simultaneously reducing the spatial and temporal redundancy. We achieve this by dynamically skipping focusing on uninformative video frames on the basis of AdaFocus, which is named as AdaFocus Plus. In specific, we add another policy network PiPrime, which has the same architecture as Pi. The outputs of PiPrime parameterize a Bernoulli distribution, which determines whether to process the local patch. PiPrime can be trained using reinforcement learning in stage 2, right after Pi has been learned. The reward function consists of 3 terms. The first 2 terms denote the gain on the ground truth confidence of activating the local CNFL. The third term compares this gain with the corresponding computational cost. Only when this comparison produces positive results will the actions of processing the selected local patches be encouraged. At test time, we simply compare the probability of the Bernoulli distribution PTB with a predefined threshold to decide whether to skip each frame. In our experiments, we first compare our method with existing works on ActivityNet. The big black dots denote AdaFocus, while different dots correspond to the varying local patch sizes. The small black stars denote AdaFocus Plus. One can observe that, compared to the best baseline ARNet, AdaFocus Plus reduces the computational cost by 2 to 3 times without sacrificing the accuracy. On FCV ID and mini kinetics, similar observation can be obtained, our method outperforms the competitive baselines by large margins in terms of the computational efficiency. An important advantage of AdaFocus is that it can be built on top of the state-of-the-art light-weighted video recognition models and further improve their efficiency. For example, here we utilize TSM as the backbone CNN in AdaFocus. Our method reduces the theoretical computational cost by 1.5 times when achieving the same accuracy. Notably, the real speedup on a VIDA GPU is 1.4 times. Here are some visualization results. One can observe that AdaFocus succeeds to focus on some task-relevant regions, such as the sailboat, the bicycle, the motorbike, the flute, and the sportsman. These results empirically validate the effectiveness of our reinforcement learning-based algorithms. For ablation study, we consider several predefined patch selection policies, such as randomly sampling patches and cropping patches from the centers of the frames or following a Gaussian distribution. An interesting phenomenon is that random policy appears strong and outperforms the central policy, which may be attributed to the spatial similarity between frames. That is to say, adjacent central patches might have repetitive contents, while randomly sampling is likely to collect more comprehensive information about the video. We also consider several variants of the reward function, and our proposed reward function significantly outperforms them. Thank you for the time.